Sorry, you can start now.
Yes, sir.
Okay.
Good evening to
So,
one and all present here for the IEEE International Webinar Series, SAVANT. I am Charulata, IEEE Student Vice Chairperson of Antenna and Propagation Society from the Department of Electronics and Communication Engineering. On behalf of St. Joseph Institute of Technology, I am here to volunteer for today's session. Now, I request Dr. C. Nyanakosilya ma'am, Professor and Head, Staff and Student Affairs to take over and address the session.
Okay, thank you, Charu. Good day, Dr. Victor and participants. This is Dr. Jnana Kausalya, Professor and Head Department of ECE, St. Joseph Institute of Technology, St. Joseph Group of Institution, India. It is my distinct honor and high privilege to welcome our guests and all participants of this day of 7th day webinar series 7 organized by IEEE APS Society, Department of ECE, St. Joseph Institute of Technology. Today, we have with us an eminent personality, Dr. Victor, Executive Director and Chief Technology Officer at PAR America, as our guest speaker. Thank you, Dr. Victor, for accepting our invitation, and we are honored with your presence here. Welcome, Dr. Victor, and our deep felt respect and gratitude to our beloved chairman, Dr. B. Babu Manoharan sir, Managing Director, Madam, Mrs. Jessie Priya, and Director Sir, Mr. Sashi Shekhar, and Principal Sir, Dr. P. Ravichandran for their unconditional support. Dear participants from various organizations, welcome you all and enjoy the maximum learning in this webinar. Welcome, Dr. Victor and all the participants. Thank you. Now the session is over to Charulata, Vice Chair APS, to introduce the speaker of the session. Charu, please take over.
Thank you, ma'am.
Thank you,
ma'am. I will be sharing a few words about our speaker. Dr. Victor VELIADIS is an Executive Director and Chief Technology Officer of Power America, which is an US Department of Wide Bandgap Semiconductor Manufacturing Institute. Dr. Victor has received a PhD degree in Electrical and Computer Engineering from Johns Hopkins University, and he is also a professor in ECE at North Carolina State University. He has given over 60 invited presentations and major conferences in India, Korea, China, Europe, and US. He is an IEEE Fellow and a distinguished lecturer in IEEE Electronic Devices Society. He had issued 25 US patents, 6 book chapters, and 115 peer-reviewed technical publications to his credit. Dr. Victor spent 21 years in the semiconductor industry, where his work includes design, fabrication, testing of silicon carbide, JFETs, MOSFETs, thyristors, and PIN diodes, as well as operations and financial planning in commercial foundry. Before we start the session, I would like to say a few instructions to be followed by the participants. Kindly post the queries and questions in the chat box. There would be a question and answer session at the end of the webinar. The attendance link will be posted at the end of the today's webinar. Now, I invite our speaker of the day to kindly start the session.
So hello, everybody, and thank you very much for inviting me. I'm honored to be here and very happy to be connecting with India. Again, I've been to India twice, and it's a beautiful country and very nice people. Thank you for the introduction. My name is John Victor VELIADIS, and I'm the Deputy Executive Director and CTO of Power America. Just to give you a brief introduction to Power America, it's a US Department of Energy Manufacturing Institute, and the goal is to accelerate adoption of wide bandgap power electronics. So power electronics made out of silicon carbide and gallium nitride. President Obama came to North Carolina State in 2015 to inaugurate the institute, and the funding is $150 million over 5 years. And what Power America does is it addresses gaps in silicon carbide and Gann power technology to create manufacturing jobs and energy savings. And as an institute, we have 55 members in all areas of silicon carbide and Gann technology. We have foundries where silicon carbide devices are being fabricated, like Wolfspeed and XFab. We have many fabless companies that design silicon carbide devices and send their designs to the foundry to be manufactured. And some of them are USCI and non-semiconductor GeneSiC Applied Materials. And then we have circuit companies that make integrated circuits in gallium nitride, like Transform and NextGen and Infineon and Gann systems. And then we have a number of companies that take these devices and put them into systems. And we have 18 universities that are part of our group. And we all work together to push the silicon carbide and GaN technology forward. So the first thing I wanted to point out is, as you can see in this graph, the semiconductor industry has been going to smaller nodes, and that's a very big development. Smaller nodes means you get more transistors per square centimeter. And at the same time, because of the smaller size, there is lower consumption of energy, which is very important. So they're more efficient. And at the same time, because of the smaller size, they can operate faster. So the trend has been to go to smaller and smaller size. And you can see by the time you get to 10 nanometers, 7 nanometers, and the latest node of 5 nanometers, only companies like Samsung, TSMC, and Intel are able to make these very small devices. And this is basically due to the fact that as you get to those very, very small nodes, the equipment, the manufacturing equipment in the foundry to fabricate the devices becomes very, very expensive and very specialized. So only a few companies are able to go to the latest node. However, there's a lot of opportunity in older nodes. And that opportunity is basically being created by the Internet of Things, artificial intelligence, 5G. There's a lot of work in quantum computing, and then there's a lot of work in power electronics. And all these areas, they have a very large volume, and they do not require the latest and greatest smaller node. So let's look at power devices. What you see on the screen to your left is a silicon carbide wafer. That's a silicon carbide wafer that I processed in the foundry in 2006. And you can see each one of the big squares you see there is a single device. And then to your right, you can see a device. So you fabricate the wafer, you test it, and then you cut it up, you dice the wafer, and you can see a single device here that's been put into a package in order for it to be tested. And this is a higher resolution image of this device here, and you can see the aluminum wire bonds. So what you need to remember here is in one device like this, if you go to the latest node for memory or logic, you would have over 1 billion transistors. But in power electronics, we deal with very high currents and very high voltages, and this whole device here is a single transistor, okay? So unlike memory and logic, where you have billions of transistors in what is really a 0.5 centimeter by 0.5 centimeter chip, here you just have a single device. And of course, these devices, because they're power devices, they're meant to control high levels of currents and voltages, can do a lot of current. You can see here that this device can easily do 80, 100 amps. And then here's the blocking voltage. That's the amount of voltage that the device can withhold, and it's close to 1700 volts. So power devices are meant to operate and control power circuits, and they can do very high voltages and very high currents, unlike the memory and logic devices in CMOS that have billions of transistors in that same area. So let's look into what makes gallium nitride and silicon carbide suitable for high voltage power applications, okay? Now, as you all know, silicon, which is shown here in the orange, is the predominant material. It's been around since the 50s. The material is very, very high quality. There are very few defects. And it can also be processed. It can be fabricated in foundries around the world at a very low price because of the very high volume. So silicon is being used for the majority of power applications. However, there's silicon carbide and GaN that are now being inserted into systems, and they're taking up some of the volume that silicon used to have. So anytime you come with a new material, you must have compelling advantages to use it, because introducing a new material can be very, very expensive, because you gotta make the wafer itself with low defects, and that's a lot of technology. And then you gotta make the devices. So if you look at GaN and silicon carbide compared to silicon, there's this spider graph here. The properties of silicon are shown here. Green is GaN and blue is silicon carbide. And you can see that the critical electric field, the electric breakdown field here for silicon, it's right here. For silicon carbide and GaN, it's 9 times more for silicon carbide and even more for GaN, okay? The second thing to note on this graph is the property of the energy gap. The energy gap in silicon is rather small. It's much, much bigger in silicon carbide and GaN. So what do those things mean practically when it comes to fabricating a device? If you look at a MOSFET that is meant for power applications, it's got a thick layer here that holds the high voltage. Now, depending on the voltage of the device you're building, you get the thickness of the layer by this equation, okay? So the higher voltage the device is meant to operate at, then the thicker the device needs to be in order to handle that voltage. And you can see from this equation that the thickness of the device is inversely proportional to the electric breakdown field, the critical field, okay? This property right here. So if you make a device out of silicon carbide instead of GaN, because silicon carbide has 9 times higher breakdown field, then the device will become 9 times thinner. And if you look at the resistance, and I'm sorry, my screen seems to have frozen. Just give me 1 second to bring it up. Sorry about that.
It's okay, sir. No problem.
Thank you. Yeah, just 1 second. The mouse not responding. Yeah, just give me 1 second, please.
Yes, sir. No problem.
Okay, I think now it's gonna be working. Okay, are you able to see my screen well now?
Yes, sir. It
Yes,
is
sir.
perfect.
Yes, sir. Yes.
Okay, sorry about that. Okay, so we were on this graph here, and now you can see the device resistance is inversely proportional to the third power of that critical electric field. So if you're using silicon carbide that has a 9 times higher critical electric field, then the resistance here of this thick layer can become almost 1,000 times smaller. So what are the properties that make silicon carbide and GaN desirable for power electronics? Number one, the large band gap allows devices to be made with low resistance. And obviously, if you have low resistance, you have lower conduction losses, right? And because of the large band gap and critical electric field, you can make thinner layers. And when the layer is thin, then you can operate at higher frequency. And that's very, very important. Okay, so just to give you an idea, if you look at a silicon device, you can see it's very, very thick. And for the same voltage capability, the silicon carbide device becomes 10 times smaller. So 10 times smaller means electrons have a smaller path to cross. So that's lower conduction losses. And then when you're operating at high frequencies where you're switching the device very, very fast, because you have a smaller path here, it switches faster with lower switching losses. So that's the big advantage of silicon carbide and GaN power electronics. And then looking at this graph one last time, you can see that the thermal conductivity of silicon carbide here in blue is much higher than the thermal conductivity of silicon, which is the competitor, and GaN for that matter. So the fact that you have higher thermal conductivity means that you can operate at higher temperatures, okay? And that's very, very important because a big part of the power electronics system is the cooling mechanism. So then cooling becomes a lot simpler to implement and a lot cheaper to implement. And of course, the higher energy band gap of silicon carbide and GaN, as shown here, means that at room temperature, you have very few thermally generated carriers. And that means that you have very low leakage current and also that you can operate at higher temperatures. So just to summarize, going from silicon, which is the predominant technology for power devices, to silicon carbide and GaN, you're able to have higher efficiency. And because the device is smaller and lighter, then the power electronics can operate at higher frequencies, and you can also operate at higher temperatures with reduced cooling, and those are very, very compelling advantages. So silicon carbide and GaN are now in production. They're being made in production, and they're being inserted into systems competing with silicon. That's not where the story ends. There are materials that have even higher energy band gap, even higher breakdown field. So you will hear down the road the next generation of power devices are aluminum nitride, diamond, and gallium oxide. And people are working intensely in those areas, but those are under research. They're still immature, and people are working to make devices and make the right materials, but they're coming up, okay? And this graph here gives you an idea of the advantage of these wide bandgap materials. This graph here shows the breakdown voltage, the amount of voltage that the device can do, and its equivalent resistance. So you see, if you want to do a device, if you want to make a device that does 1,000 volts, if you're going to be using silicon carbide, your resistance will be right here for the 1,000 volts. If you use gallium nitride for the same 1,000 volt device, you can make that device with low resistance. If you go to diamond, it's lower. And then of course, aluminum nitride is even lower, and silicon of course is very, very high. Okay, now silicon of course is not dead, because as I mentioned before, silicon is very mature, it's very cheap, and it can be processed in fabs, foundries around the world at a very low cost. So it's a very big competitor. So where do the different materials have applications? If you look at the frequency right here versus the power, then you can see that at low frequencies, silicon devices, the IGBT, the MOSFET, and modules do very, very well. It is when you go to higher frequencies that silicon is a lot more lossy, a lot less efficient, and that's where you have silicon carbide devices and module. And GaN, of course, has an even higher figure of merit, so GaN can go into higher frequencies. So if you look at power devices, in under 650 volts, silicon is very, very strong, and also GaN is competing very effectively in that area. If you look at devices that are 900 volts and beyond, then it's really silicon carbide, where devices have been shown at 1200 volts, 1700 volts, all the way up to 10,000 volts. And the big area of competitions, the big battleground, is this area right here at 600, 650 volts. The 600 volt area has very large number of applications, so it's got a lot of volume, and silicon is very, very effective because it's very cheap. GaN can also be made well at 600 volts. It's a good competitor, and of course silicon carbide is also very capable at 600 volts. So for the big application area of the 600 volts, silicon carbide, GaN, and silicon carbide and GaN and silicon compete very, very effectively. And it's just a matter of what your application considerations are to select the right device in this area. Beyond 900 volts, clearly the selection will be a silicon carbide device. Okay, so what is the advantage of using silicon carbide? Because you're able to do higher frequency and you're able to go at higher voltages, that simplifies the design of the circuit. So you have fewer levels if you're trying to do silicon carbide work. And because you're going to higher frequency operation, then you reduce the magnetics. Instead of having large magnetics, you have much smaller magnetics. And of course, because silicon carbide has very high thermal conductivity, then you're able to make a smaller heat sink and reduce the packaging. So those are the advantages of silicon carbide compared to the dominant silicon technology. So where do those advantages play a role? If you look at this graph here, you can see that at lower frequencies, silicon does very, very well, and it's a very efficient material. Now, once you go beyond this red line here, meaning you're going at higher frequencies and high powers, that's where silicon carbide and GaN have a big opportunity to succeed because of their higher efficiency and because of the limitations of silicon. So what applications are in this high frequency, high power area? You have high voltage DC transmission. You have traction, which is basically what you're putting into electric vehicles, the AC motor, driving the AC motor. You have AC type of transmission, motor drives, power supplies, lighting, and automotive. So there are a lot of applications in this space here. So the biggest application for the United States is the aerospace sector because of the very large aerospace industry, and the power electronics with silicon carbide and GaN can play a big role in this sector. The automotive sector, it's a very massive sector now that automotive is moving towards electrification, either hybrid vehicles or full electric vehicles, and silicon carbide and GaN can play a big role. Then you have the grid infrastructure. Grid infrastructure is basically transporting energy either from solar areas or from wind farms to the cities where the area is going to be consumed. And silicon carbide electronics are more efficient in these applications. And electric motor drives, which are, I'm talking about the motor drives that are very, very large, those can greatly have their efficiency increased with the use of silicon carbide. And finally, data centers. You all know that the use of Facebook, Instagram, and even what we're doing today, all this information that's being exchanged, you need data centers, and data centers can become far more efficient with the use of silicon carbide. So if we were to take a quick look at the aerospace sector, in the aerospace sector, the advances are primarily power electronics and energy storage. And what we're doing today is we're replacing systems that use fluid, okay, with solid state power electronics. So we're changing hydraulic systems and air systems into solid state power electronics. And eventually we want to go to the more electric engine, and finally the all electric aircraft. Now, there are aircraft that are all electric today, but they're very small and they're meant for small distances. It will be many, many years before we see these big aircraft that go across the Atlantic or the Pacific being fully electric. So what's the advantage of silicon carbide in the power electronics of the aircraft? Because silicon carbide, the devices are smaller, because their cooling mechanism is smaller, then the weight of the power electronic system with silicon carbide becomes lighter. And of course, in an aircraft, the weight is very, very important. You want to minimize the weight of the equipment so you can fit more people. And also, if you replace hydraulic systems where you really have fluids running with power electronics, that helps you with reliability and maintenance, because it's very hard to control systems with fluids. The maintenance is more expensive and the cost is more expensive. So what do we get from aircraft electrification using silicon carbide? We have better fuel efficiency. We have lower cost for maintenance and operation. Because we've eliminated the hydraulic systems, the reliability is higher. And because it's electric, there's less noise and lower emissions. And all of those are compelling advantages. But again, the application in aircraft is many, many years away. Now, let's go into the biggest application for silicon carbide, where silicon carbide is being used today as we speak. So what I'm showing here is an early electric vehicle. So this is an all-electric car from 1914. And this electric vehicle was the car that the wife of Henry Ford was using. So as you know, Henry Ford came up with the assembly line, and he greatly reduced the cost of making cars. And he selected the internal combustion engine, you know, a gasoline-powered car. But in the early days of automotive, steam cars, electric cars, as well as gasoline cars were all available. And you can see all the technology was there, you know, the battery stack. But the electric car did not win back in the early 1900s because there was a problem with range. The batteries would not give you a lot of range. And in 1914, most people did not have electricity in their home, so it was very difficult to find a place to charge the batteries. And for those reasons, the internal combustion, the gasoline car, won that race. And of course, it was a huge step that Ford did. By doing the assembly line, he reduced the cost of the vehicle almost 10 times. So since he was making gasoline vehicles, the cost of electric vehicles was far more expensive. But what I'm trying to point out here is that electric vehicles have been around for over a century. It's just that people decided to use the gasoline cars because of certain advantages at the time. Now, there have been $350 billion of investments announced in electric vehicles. All major vehicle companies are moving towards a fully electric battery operated vehicle. So there's a lot of opportunity there. And you can see Tesla, which is basically a very innovative electric car company in the United States. In its motor drive here, in its inverter, it is using silicon carbide, not silicon. Okay, so there's about 1 million silicon carbide devices that are on the road in cars, in Teslas, in the United States and across the world. Okay, so this was a very big step that Tesla did to replace the mature and well-known and reliable silicon with silicon carbide. And the big advantage of using silicon carbide is because it's got higher efficiency, it allows the electric car to have bigger range for the same battery size. So that's a very, very important, because if you look at electric vehicles, the range is one of the biggest considerations when people are deciding to buy an electric car. So going into the electric grid applications, as I mentioned before, high voltage DC transmission, AC transmission, microgrids, solar, wind, these are all very important applications that can be made more efficient with silicon carbide. And about 40% of the electric energy that's being generated passes through power electronics on its way to the point of use. And you can see here a good example of the work on high voltage DC transmission is in China. And if you transmit in DC transmission makes sense if your distance is over 600 kilometers. So if you're going to transport energy from a solar farm or a wind farm or a hydroelectric plant over 600 kilometers, then DC transmission is more efficient than AC transmission. And if you look at China, there's a lot of energy that's being created here in the northwest of the country. And this energy needs to be transported into the big centers here in the East, where the consumption and the industry take place. So they've created 1.1 kV DC line. So that's 1.1 megavolt DC line, very, very high voltage, very high distances to transport the energy. And if you look at silicon carbide, I'm showing this wafer here again, and each one of these is a device. This here is a little test area because this is a test wafer, right? And I'm trying to figure out properties. So I have these test patterns everywhere to study. But this here is the device. And if you want to go very high in current, you got to take many of these devices and put them in parallel in a module. And that's what is being done for silicon carbide. However, if you look at silicon, because it's such a good material and the whole wafer is defect-free, they can make a whole wafer as a single device. So in silicon carbide, because it's a newer material, the wafer has defects, and as a result, you cannot use the whole wafer as a single device. In the case of silicon, you can use the whole wafer. So a lot of the work that's being done in silicon carbide is basically to get to the point where the wafer has very few defects, and that's very challenging. Okay, and just to give you an idea of the capability of silicon carbide, this is a single device, a single transistor, and you can see the dimensions. It's 9 millimeters by 9 millimeters, and it's capable of doing almost 28,000 volts. So this single transistor, if you apply 28,000 volts to it, it can handle that current without breaking down or burning. So it's got a lot of capability for high voltage applications that are being developed. Okay, when it comes to electric motors, you see these big installations here. They're using very massive motors. And if you make motors in the traditional way where the frequency is fixed, you're wasting about 20 to 40% of the energy. Okay, now if you and I will point out that across all the sectors, electric motors account for about 40% of total electricity used in the United States, and it's about 60% of the electricity used in Europe. So it's a very high, use for electricity in motors. So what you want to do is you want to go from the fixed frequency motor to the variable speed motor, and that will make it more efficient. If you make it out of silicon, the traditional power material, it's very, very lossy. If you follow the silicon carbide solution, you can go directly from the high voltage grid from 14,000 volts into a variable speed drive that's being enabled by silicon carbide, and then you have a variable speed compressor for the motor, which will save you a lot of energy. So that's another big application for silicon carbide. And finally, everybody knows about data centers. This is the largest data center, or the second largest data center in the world, in China. It's got 360,000 servers. And as you can imagine, there is a huge amount of heat that's being generated in this data center. And waste heat management is very, very challenging. So there are several approaches to taking care of that heat problem. One of them is using quantum computing to increase the efficiency. The other one is to use silicon carbide and Gann for the power electronics. You can use materials that have high density storage. You can use innovations in the cooling, like liquid and immersion cooling techniques, and so on and so forth. But the bottom line is, in data centers, where there's a huge demand between all the photographs, the Facebooks, the social media, and also all the companies storing their data, there are many, many very large data centers, and the heat that's being generated is massive. And silicon carbide and Gann is one of the approaches that are being used to make more efficient data centers. So an example of a data center architecture would be the high voltage side would use silicon carbide, which is very well suited for high voltages. And then in the low voltage side, you would use gallium nitride power electronics that does really, really well in the below 600 volt area. And here are some circuit configurations to basically design more efficient data centers. Okay, so moving forward, I think I have shown you that the biggest application for silicon carbide is the one of electric vehicles. So it's expected that in 2024, it will be almost a $2 billion market for silicon carbide, and about 50% of that market will be going into vehicle applications. And you got to keep in mind that what will make a new technology cheaper is going into volume production, going into large production. And in order to go into volume production, you got to find one application where your specific new technology makes a big difference. So for silicon carbide, the big application that will lead to a large demand is in the electric and hybrid electric vehicles. And as you all know, when you go to high volume production, that's when prices start to drop, and that's when silicon carbide can become very, very competitive with silicon. So that's the big application for silicon carbide. And this is basically a graph. We're in 2020 today, but going out to 2025, the silicon carbide device market alone is expected to be a 3.2 billion market. Okay. All right. So let's look at how you make the substrate. In order to make a device, you need to have a wafer to start with, a substrate. Now, in silicon, there's a very efficient process to make wafers. It's the silicon liquid phase growth. It's got this necking area here from the seed, and that helps eliminate the defects. And you need about 1500 degrees to make the silicon wafers, which of course are made very cheaply and in large quantity. In silicon carbide, however, the material doesn't melt until 2800 degrees. So that's a very, very high temperature. It's about half of the temperature of the surface of the sun. So what I want to point out in this graph is when you make silicon carbide wafers, which is the starting material that you will take into the foundry to make devices, the process to make the wafer is more complex, and that translates to a higher cost. And also the way it's being made in silicon carbide, you start with a seed wafer, so that will allow defects from the seed wafer to propagate into the new wafers you're building. So if you look at the silicon carbide substrate, which is the wafer right here, the substrate, you start with a substrate in this process that I just showed you in the previous page, which is more complex and therefore more expensive than silicon. And then you put an epitaxial layer, which is a high quality layer where the device is going to be built. And the idea behind doing the epitaxial layer well is to make sure that defects in the substrate do not propagate into the epitaxy. Okay, so there are several defects in silicon carbide. And again, I will point out that silicon is a very, very clean material, and that's a huge advantage. It's been around for 60, 70 years, and it's been perfected in its growth. But for silicon carbide, there's threading edge and screw dislocations that tend to be benign. They do not cause a problem. There are larger defects like carrots, triangles that have been mostly eliminated. The one defect in silicon carbide today that's actually being a problem with making high voltage devices are basal plane dislocations. And basal plane dislocations can degrade performance. So that's the one defect that's shown here, BPD, basal plane dislocations, that the silicon carbide community is trying to eliminate. And if you look at the wafer cost, back in 2001, a 2-inch wafer was $5,000. And with years of production, with technology improvement and larger volume production, we've come now to having 6-inch silicon carbide wafers in production, and the cost is about $600, $700. So the price has gone down substantially from the old days where very small wafers would cost a big amount of money. However, the cost is far more expensive than the cost of silicon. Silicon wafers are about $20 a piece. With silicon carbide, it can be $600 and maybe a little lower in volume production. So that's a big problem, because when you have silicon and silicon carbide technologies competing, the cost is a very important consideration. People want the additional better performance, but they don't want to pay a high cost for that. So if you look at silicon carbide wafers, we're right here, 6-inch, 150 millimeters. and 200 millimeter wafers have been fabricated, but they're not in production. They're basically in the stage of research. Now, if you look at silicon, just for a comparison, silicon was making 8-inch wafers back in 1992, and 8-inch wafers for silicon carbide are expected over the next 2 to 3 years. So basically, silicon carbide wafers with respect to area are about 30 years behind compared to silicon. And the size of the wafer makes a big difference. This graph here shows the reduction of cost. And of course, this is a relative graph. It shows you cost at 100% in 2011. And you can see how moving into 2016 and beyond, the cost has dropped about, below 20% of the original cost, right? So that's a big improvement over the years to reduce the cost. And you can see that has to do with the size of the wafer. So if you go back in the earlier days, assuming that a 75 millimeter wafer was available, when you get to 200 millimeter wafers versus the 75 millimeter wafers going to larger wafer size along the way, then you get 7 times more devices out of your wafer because of the bigger size. And processing a wafer in the foundry, whether it's a small wafer or a large wafer, the cost is the same. So you get a huge advantage by going into larger wafers. So a lot of the work that's being done in silicon carbide is to make the wafer larger to reduce the cost of the devices. Okay, so where's the cost today? The cost of silicon carbide is about, you see here in these curves, the cost of silicon carbide is about 3 times more than silicon. So silicon carbide devices are 3 times more expensive than silicon. That's where we are today. But if you look into applications at the systems level, when you make a system made out of silicon carbide, that is now more cost effective in certain applications than silicon. If you look at the total cost of a photovoltaic inverter system, you can see that if you use silicon, it's right here. If you use silicon carbide, it's lower. The semiconductor itself, the silicon semiconductor, okay, versus the silicon carbide semiconductor have a price difference of 3 times. So the silicon carbide semiconductor is 3 times more expensive than the silicon semiconductor, but the overall system for silicon carbide is lower. And this is because you're able to operate silicon at higher frequencies. This is basically the magnetics for silicon operation, which is limited to lower frequencies, 20 kilohertz. When you get to silicon carbide, where you go to 100 kilohertz, then as you can see, this becomes a lot smaller and a lot lighter and therefore a lot cheaper. So the bottom line is you're going to pay more money for the silicon carbide device, but because the silicon carbide device will bring a lot of simplification in the overall system, at the system level, it's already cheaper to use silicon carbide in several applications. And you can see this here one more time. When you're at the lower frequencies, your magnetics need to be very, very big. When you operate at very high frequencies where silicon is not capable of operating, then the magnetics become a lot smaller. So you have a reduction in cost, weight, volume, and of course, reduction in losses. You have a far more efficient system. And that's the selling point of silicon carbide. You have to look at the systems level when it comes to cost. Okay, so some information about the silicon carbide material. It comes in many, many polytypes. And the most popular polytype is the 6H and the 4H structure. And almost all silicon carbide power devices are made with the 4H configuration. And you can see that here with the planes, there's the carbon plane, and then there's the silicon plane. And it's a 4H structure. And silicon carbide wafers are being cut from the boule at an angle of 4 degrees to minimize defects. Now, silicon carbide is an indirect bandgap semiconductor. So a direct band semiconductor means that when you go from the conduction, you have a direct conduction to valence band. And when you have a conduction to valence band transition, obviously, if it's radiative, you're going to generate light. In the case of silicon carbide, it's an indirect bandgap semiconductor. So you have to have both conservation of energy and conservation of momentum in order to produce light. So this is a silicon carbide device that I had made and put in a package. And you can see when you bias the device, it produces a little bluish, blue-purple light. So there was a time when silicon carbide was basically being researched as a photonic material for to build the blue light laser. And as we all know, the blue light laser, semiconductor laser, that battle was won by gallium nitride. But nevertheless, silicon carbide does produce light because its band gap is in that ultra, low ultraviolet and blue-purple range. So devices in silicon carbide and in general power devices can be made lateral or they can be made vertical. If you make a lateral device and you want high voltage, the higher the voltage, the bigger the separation between the gate of the device and the drain of the device. So when you get to a certain level, which is about 900 volts, this separation becomes so big that if your device on the wafer is lateral, it's taking too much space on the wafer. On the other hand, if you make a vertical device, like the ones that I'm showing here, then this gate to drain separation happens vertically. So you don't take a lot of space on the surface of the wafer. And that will allow you to have more devices per wafer, which will make the cost a lot cheaper. And again, for vertical devices where silicon carbide devices are almost all vertical, you can see that the amount of voltage that the device can hold has to do with the thickness of this layer and the doping of these layers. And the equations here give you the optimal conditions. So suppose you want to make a device that will do 1,000 volts. You put 1,000 volts here, you put the critical electric field of silicon carbide. This will tell you the thickness of this layer and the resistance that you're going to have. And also, this equation tells you for a specific voltage that you're interested in and the critical electric field of silicon carbide or whatever power material you're using, this is the optimal density, doping density. So you have the thickness, the doping density, and the resistance of the layer through these equations. And just to give you an example, if you want to make a device that will do 2,000 volts, this layer needs to be about 12 microns thick. If you want to make a device now that will do 10,000 volts, that's able to withstand 10,000 volts, then the thickness of this layer needs to be 90 or 100 micron, roughly speaking. Okay, and then there's the concept of unipolar versus bipolar devices. In a unipolar device, power device, you only have one type of carrier doing the conduction. So this here would be only electrons, right? So your resistance is given by this equation here. This is the thickness of your layer, and this is the doping and the electron mobility of the electron. So in these types of devices where you have a single carrier, this is the resistance, and because you only have electrons or holes doing the conduction, then the device can switch a lot faster. Now, a second type of consideration is a bipolar device. If you look at a bipolar device, you got both electrons and holes going through the device. So now your resistance is a lot lower because the resistance is divided both by the electron contribution and the hole contribution. However, the fact that you now have both electron and holes means that when you switch the device from on and off, it's going to be slower because you got two types of carriers that you need to sweep out. And the fact that it's slower means you got higher losses. So the bottom line is if you make a device as a unipolar device, as shown here, you only have one type of carrier, your conduction losses will be a little higher, but your switching losses will be very low because switching is fast. If you make a bipolar device, then you have both electrons and holes doing the conduction. So that means the resistance is lower, but your switching losses are higher. So the bottom line is, depending on your application, if you make a device, let's say from up to 6,000 or even 10,000 volts, making a unipolar device in silicon carbide makes sense. If you go for a device beyond 10,000 volts, it has to be a bipolar device like an IGBT. So that's the consideration, unipolar versus bipolar devices. And you can see unipolar devices like MOSFETs, both planar MOSFETs and trench MOSFETs, JFETs, and diodes, which are unipolar. They've been fabricated in silicon carbide. And bipolar devices like the bipolar junction transistor, the thyristor, IGBTs, and PIN diodes have also been fabricated in silicon carbide, but almost 95% of all devices in silicon carbide fabricated today are MOSFETs. That's the device type that has won. So just to give you an idea between the planar and the trench MOSFET, in the planar MOSFET that's shown here, you have the channel resistance right here, and then you got this JFET resistance here. If you go to the trench MOSFET, then you eliminate this JFET resistance. There's no, the conduction is happening in this vertical direction, but the problem is because it's a trench, the corners of this trench are susceptible to high voltage issues, okay? So there's two types of MOSFETs that are being made in silicon carbide. One of them is the planar MOSFET, and the second one is the trench MOSFET. And the idea is that the trench MOSFET for up to 1700 volt devices has lower resistance because you're eliminating this JFET region right here. Okay, so two types of MOSFETs in silicon carbide. And this is a graph that shows you the resistance of a silicon carbide MOSFET as a function of voltage. You can see here, for example, if you want to make a 1000 volt device, then the resistance of this drift layer is shown right here. And then here are the other contributions in the overall resistance of the device. So this is the resistance of the substrate, which is down here. You have the resistance of the channel of this area here. You have the resistance of the JFET, this narrow corridor here. And then you have the resistance of the contacts, the source contact, the drain contact, the gate contact. So if you want to make a 1000 volt device, you can see that the higher contribution to the resistance comes from the substrate. The second highest contribution is the channel, and then you have the drift layer, which is the thickness of this layer right here. And then you got the JFET region and the channel region. However, if you make a 10,000 volt device, you can see because this layer has to be very thick for 10,000 volts, that the biggest contribution comes from that thick drift layer, and then the substrate and the channel are lower. So if you look at the total resistance, you can see that if you're below maybe 2000 volts, right? The contribution of the substrate and the channel play a role. But by the time you get above 2000 volts, and if you look at 10,000 volts, for example, the total resistance from the device comes pretty much from the thickness of this thick drift layer. So depending on whether you're making a 1000 volt device, 2000 volt device, 6000 or 10,000 volt device, these are the resistive elements, and that tells you what you need to optimize. So for the 1200 volt applications, which is a very major area right here, you can see that since the substrate is your biggest resistance, then you want to make the substrate thinner. You want to thin the substrate to reduce this resistance, and you have to be very careful in how you design your channel. You want to design your channel to be as low resistance as possible because it's still a big portion of the overall resistance. If you go to 10,000 volts, the substrate and the channel contributions are basically negligent, right? The big contribution at 10,000 volts, almost all of the resistance comes from the thick drift layer. So we have ways of, the bottom line is depending on the voltage rating of your device, then you do the design of the device accordingly to reduce the resistance. So another thing we need to take into consideration when it comes to power devices is the electric field buildup. This is a PN diode, and you can see at the corner of the device, the electric field becomes very strong. It becomes dominant. So the idea is that you have a high breakdown voltage here, theoretically, based on the thickness of this layer, but you're not going to get to that voltage because you got breakdown at the corner of the device at the surface. So what you want to do is you want to take that electric field and spread it out. And there's several techniques to do this. People use metal field plates. They do a beveled edge. They use guard rings or junction termination extensions. So that's very, very important in silicon carbide and all power devices. And you can see in this graph here that shows breakdown voltage versus resistance. I made two devices that were identical. The only difference between those two devices is one had an edge termination and the other did not. So in one case, the problem of this electric field buildup was basically alleviated with the edge termination. In the other case, it was left as it is. And you can see if you put no edge termination, the device will only do 450 volts, right? It won't get to the total capability, the theoretical capability of the thick layer. If you do a good edge termination, that same device will get to 2000 volts. So that's the advantage of using edge termination, and all devices, all power devices will have an edge termination because of that critical electric field problem. So I'm going towards the end of my talk, and what I wanted to show here is a big part of making a device successfully and at low cost is having streamlined fabrication. Now, as I mentioned before, silicon has been around for 70 years. It's being made in foundries across the world, and the fabrication of silicon devices is very streamlined and efficient. So when you come to fabricate silicon carbide devices, you want to take everything that applies from silicon. You don't want to reinvent the wheel, okay? But there are certain processes in silicon carbide that you cannot use from silicon. So the areas where you need to develop technology for silicon carbide fabrication is the etch, because silicon carbide is inert, so you cannot have a wet etch, you can only have dry etching, and that dry etching is very, very slow, but silicon carbide is a very hard material. The second thing you want to be able to do is thin the substrate. As I showed before, the substrate resistance can be a big contributor to the overall resistance. So you have to have techniques to thin the substrate. Obviously, to make any semiconductor device, you need to be able to dope, so you can get P regions and N regions. And in the case of silicon carbide, doping can only be done by implanting. Thermal diffusion, which is possible in silicon, does not apply. Metallization, the coefficient of thermal expansion of silicon carbide is different than that of silicon. So when you make a silicon carbide device, you gotta select metals that have close thermal expansion coefficients in order for the device to operate at high temperatures without being destroyed. When it comes to the ohmic contact, if you look at silicon, if you deposit a metal, you can get a good ohmic contact. In silicon carbide, because of the high band gap, you don't get an ohmic contact when you deposit metal. You get a Schottky contact, and you have to come up with a process to make a low resistivity ohmic contact. In the case of silicon carbide MOSFETs, you have a gate oxide, and it's important for that gate oxide to be clean so you can have high mobility and you can eliminate instability. Another consideration with silicon carbide wafers is because of their band gap, they're transparent. So in the case of silicon, because of its lower band gap, it's opaque. So there are a lot of tools that use photonics and beams, photonic beams in the foundry to inspect the wafers. So tools that are made to do inspection for silicon will not work for silicon carbide because the silicon carbide wafers are transparent. So that's another area of consideration. And another issue, of course, is silicon, because it's a very streamlined, almost zero defect type of wafer. It's very, very flat, and that's not the case in silicon carbide. And of course, in silicon carbide, you don't have a good thick thermal layer that you can create, unlike silicon. So you need to deposit, oxides and dielectrics, and deposit dielectrics contain defects. So you need to be aware of that and work around it. So if you look at the doping, nitrogen and phosphorus are the N dopants, and aluminum is primarily used for a P dopant. So those have been are known and well understood. And I wanted to give you an idea of implantation, which is the very big difference with silicon. In silicon carbide, implantation has to be heated in order to minimize the crystal damage. And you can see this is a silicon carbide piece of wafer before implantation. And you can see that it's transparent as expected. So after you do the implantation, where you have this bombardment of ions to implant, the wafer looks like this, okay? So you've basically destroyed the crystallinity of the wafer. And in order to take care of that problem, you need to do a very high temperature anneal to basically recrystallize the wafer. And when you do the anneal, and this is just some interesting specifics of silicon carbide fabrication examples, if you do the anneal of a silicon carbide wafer at 1600 or 1700 degrees, in order to activate the dopants and in order to recrystallize the wafer, if you don't use a proper protective layer, your device will look like this. If you do use the right protective layer, then your device comes out well. So this was a device or a wafer where no protective layer was put on top of the wafer when we went to that 1600 degree anneal. And this is a wafer that did have a protective layer. Obviously, none of the device on this layer, on this wafer worked. And you can see how nice and clean it looks after the anneal when you use the correct protective layer. And there are several options for protective layers. And this is part of the technology you develop in order to process a new type of material in a foundry. Okay, and the last thing that I wanted to talk about is the module and the package. So basically, you fabricate a device, and then it has to be put into a module before it goes into the system. So I wanted to bring your attention to the fact that with silicon carbide, you have high voltage, you have high current, you have high temperature, and high frequency all at the same time. So if you use modules that were made for silicon, they will not work well. You will not be able to take advantage of the great performance of silicon carbide. So it's a big opportunity for module development where you need to build modules specific for silicon carbide, meaning modules that can do high voltage, high current, high temperature, and high frequency. So there's a lot of developments and a lot of innovative work happening in modules. You want double-sided cooling. You want to be able to cool from the bottom and the top in order to extract the heat. You want to basically, if you're going to use wire bonds like here, they have to be very short. And, you know, it's a good idea to get rid of wire bonds altogether, to use tabs, because wire bonds introduce inductance. And when you operate at high frequencies, inductance is a huge problem. You want to do innovations in the heat sink and base plate to extract the heat. You want to encapsulate the device with some sort of gel that will do both high voltage and high temperature. You want to make innovations in die attachment and basically calculate all the thermal interfaces. And if you want to make a comparison, if you take a silicon carbide device and put it into a silicon module, it's like making a very capable Ferrari engine and putting it in a small car, right? You will not get the performance. So a lot of work needs to be done in silicon carbide module to take advantage of the properties of the device. And with that, I will thank you for your attention. And I have concluded my talk, and I'm open to your questions.
Sir, thank you for your fruitful and informative session. Sir, thank you, sir. Sir,
Absolutely.
shall we move on to the question and answer session? Hello, sir.
Yes.
So moving on to the first question, why direct current internal resistance value changes in the battery?
So the work that I'm doing is not related in the batteries, and the idea is that you want to have batteries that will have, number one, will be very reliable. You don't want a car breaking down because the battery is a problem. And number two, you want to be able to store a large amount of energy in the battery. So today, different lithium-ion technologies are the best technologies for the battery, but I'm not a battery expert. But what I can tell you is if battery development does not continue to happen in order to give you the range, then materials like silicon carbide and Gann that are being used in electric vehicles will not see the high volume that is expected.
Okay, sir. Okay, sir. So moving on to the next question. How is the chip industry progressing nowadays in terms of manufacturing and in business levels?
So with respect to manufacturing and with respect to manufacturing silicon carbide in foundries, as I showed before, very few companies have the billions of dollars required to make the very small nodes, like Samsung and Intel and TSMC, to get the 5 nanometer and 7 nanometer nodes. Now, it is a good thing that silicon carbide, because you're making large power devices, does not require the high resolution of the latest mode. So you can take a foundry that's about 30 years old, and the steppers in that foundry, which is a very expensive item, will work just fine for silicon carbide. So even 20 to 30-year-old steppers will work very well with silicon carbide. And most of the tools in what is a fully paid, I would say even obsolete foundry, are perfect for silicon carbide. So the bottom line is, if you take a silicon foundry, because obviously the majority of foundries in the world process silicon, if you take a silicon foundry and you want to put silicon carbide production in that foundry, it's basically an investment of $15 million or so to get there. And as an example, it takes billions of dollars to build the latest node foundry. So the bottom line is, a lot of the older silicon foundries that are available around the world can be used and are being used to produce silicon carbide devices together with the older generation of silicon devices.
Yes, sir. Moving on to the next question. What is the impact of power electronics in environment?
Okay, so that's an excellent question, because it's a very, very hot topic. So the biggest advantage of using silicon carbide power electronics, or GaN power electronics, is the higher efficiency. If you have power electronics with higher efficiency, that means you're generating less CO2, you're polluting less. So one of the big drivers of, one of the big drivers of electrification in electric vehicles is that they're far more efficient than combustion engine gasoline vehicles. So there are much fewer emissions. Now, if you change silicon power electronics with silicon carbide power electronics because of the higher efficiency, okay, you're basically polluting even less. So one of the biggest drivers of using silicon carbide power electronics is basically the environmental benefits. There are huge environmental benefits that come from the fact that systems with silicon carbide can be made far more efficient than systems with silicon. But having said that, if you look at vehicle electrification, even going to a silicon traditional electric vehicle, okay, you're making a big difference on the environment, because the electric motor is far more efficient than the gasoline motor. So one of the big drivers, so the bottom line is, as you all know, when you come up with new technology, people will invest and they want to make money, right? It's all about the business case. It's all about making money. So in silicon carbide, you will make money because you're making, let's say, vehicles that have a longer driving range, okay, which makes the battery, cheaper, right? Or you can use fewer batteries, smaller battery size because of that higher efficiency. But one of the very good outcomes of using silicon carbide is, because of that higher efficiency, you are protecting the environment. And that's a big, big consideration.
Okay, sir. Thank you, sir, for answering all the questions promptly. Now I invite Dr. G. Rohini ma'am, Professor and Head, Lab Affairs, to express her gratitude.
Thank you, Charlotta. Good morning, Dr. Victor.
Good morning.
Good morning, sir. Very good evening to all. Myself, Dr. Rohini, Professor. It gives me immense pleasure to deliver the vote of thanks for this webinar on behalf of Department of ECE, St. Joseph Institute of Technology, St. Joseph Group of Institutions. Technology enables every one of us to work every minute of every day from anywhere in the world. First, I would like to thank our guest speaker, Dr. Victor, Executive Director and Chief Technology Officer at Power America, Professor ECE, North Carolina State University, USA, for his galvanizing speech on accelerating commercialization of Silicon Carbide, Gann Power Electronics. Thank you, sir, for finding time and giving information on applications of silicon carbide, such as electric car vehicle, advances in power electronics, selection of right devices, and manufacturing process of silicon carbide and its commercialization, despite your busy schedule for this SAVANT webinar series 2020. My heartfelt thanks to our beloved chairman, sir, Dr. B. Babu Manoharan, for his consistent upkeep in conduction of this webinar. My sincere thanks to our Managing Director, ma'am, Mrs. B. Jayashipriya, and our Director, sir, Mr. B. Sashishekar, for their guidance in conduction of this webinar. I would like to express my gratitude our Principal, sir, Dr. Ravichandran, for his support to conduct this webinar. I also thank our Head of the Department and IEEE Chapter Advisor, Dr. C. Gnanakausalya, and all other faculties of our department for organizing this event successfully. A special mention of thanks to our student chair, IEEE Photonics APS Society Chair, Ms. Harita Kea, and Student Vice Chair, Ms. Charlata, third year EC, and all other IEEE students for aiding in conduction of this webinar. Finally, I thank all the students, faculties, research scholars from India and other countries for their active participation in this webinar. Thank you all. Thank you, sir, once again.
Thank you so much. I appreciate the opportunity. If anybody would like a PDF of the presentation, please let me know.
Sir.
I will be happy to send out. And I do hope that your students and everybody benefited from the presentation. Thank you so much again for having me. Thank you for your hospitality.
Yes, sir.
Thank you,
sir.
I again like to thank Dr. Victor Veliadis for taking out his time from his busy schedule and joining us to share his knowledge. Thank you, sir.
Thank you. Appreciate it. Appreciate it. And have a great night. I guess in India, it's still daytime here in the United States.
Thank you.
Yes, sir.
Thank you, sir. Thank you for your valuable time. Thank you.
Bye-bye.
Bye, sir.
Bye, sir.
Bye, sir. A heartful. So the PPT. Sir, is the PPT was shared?
Are you announced?
Hello.
You can start, Saru. Yes. Okay. A grateful heart is a magnet for miracle. Here we are at the end of IEEE International Webinar Series, SAVANT. I would like to take this moment to thank our entire IEEE team. First and foremost, my heartfelt thanks to our beloved chairman, sir, Dr. B. Babu Manoharan, for his consistent upkeep in conduction of this webinar. My sincere thanks to our managing director, ma'am, Mrs. B. Jayashipriya, and our director, sir, Mr. B. Sashishekar, for their guidance in conduction of the webinar. I would like to express my gratitude to our principal, Dr. P. Ravichandran, sir, for his support to conduct this webinar. I also thank Dr. C. Gnanakausalya, ma'am, head of the department, IEEE Student Chapter Advisor, and Dr. Rohini, ma'am, professor and head, Lab Affairs, IEEE Coordinator, for guiding us throughout the SAVANT webinar series. I would like to specifically thank IEEE Staff Coordinator, Mr. J. Bino, sir, for being the backbone of this event, SAVANT. I also thank all the ECE staffs for their constant support. I would like to take a few more minutes to thank each and every one of us SAVANT team. I am extremely thankful to Ms. J. Meera, IEEE Student Chairperson of RIA Society, and Ms. Sanjana K.E., IEEE Student Chairperson of EMBA Society, for bringing in eminent speakers to share their knowledge. It is very difficult to get international speakers, and it is also complicated to fit them into our slots. They did that quite smartly to make it as a sequence. Thank you, Sanjana and Meera. I would like to thank the content writer for SAVANT webinar series, Ms. V. Dharani, IEEE Student Chairperson of WIE Society. I would like to thank Ms. Sriniveda, IEEE Student Chairperson of Photonics Society, for WhatsApp and Telegram communication. I would like to extend my thanks to Mr. Selva Madhavan, IEEE Student Vice Chairperson of BTS Society, Ms. Sivanyana Soundarya, IEEE Student Vice Chairperson of WIE Society, Ms. Saraswati, IEEE Student Vice Chairperson of EMBA Society, Mr. Subhash, IEEE Student Chairperson of RA Society, Mr. Nikhil Madhavan, IEEE Student Chairperson of BTS Society for email communication and certificate distribution. Thank you all. Our special thanks to the certificate and poster designer, Mr. Dhanush, second year student, EC department, for his endless help and contribution to this event. All the SAVANT webinar series will be available in our official YouTube channel, St. Joseph's Institute of Technology, Department of ECE. Our next IEEE International webinar series, SAVANT 2.0, starts from June 23rd with more interesting topics from eminent speakers all over the world. Interested participants can register in the link provided on the session and attend the session. Thank you all.
Thank you, Charlata.
Thank you, ma'am.
Thank you, other students.
Thank you. Sanchana,
Yes, sir.
please transfer the host control to me.
Yes, sir.